Density altitude can be a difficult concept. Even the definition of density altitude, that it is pressure altitude corrected for non-standard temperature, provides limited clarity. The following primer explains density altitude and demonstrates how it affects aircraft performance. As learned in science class, air has weight, and although a person might not be able to feel it, this weight of air exerts a force on the surface of the Earth. Generally, we describe this force as pressure. On a standard day, the temperature at sea level is 59 degrees Fahrenheit, and the atmosphere applies 14.7 pounds per square inch, which causes a column of mercury within a barometer to rise 29.92 inches. As altitude increases, the atmospheric pressure decreases. With less pressure exerted on the mercury pool, less mercury is pushed up the tube, indicating a lower barometric value. More atmospheric pressure yields a higher barometric value. What we learn is that an increase in altitude causes less pressure and a lower barometric value. However, weather changes, and we cannot only fly on standard days where temperature is 59 degrees and barometric settings are 29.92. To compensate for temperatures that are other than standard, we calculate density altitude. In order to understand the relationship between pressure and density, we use the ideal gas law, where P is pressure, V is volume, N is the amount of molecules, R is the ideal gas constant, and T is temperature. To get to density, we divide the equation by volume and, along with some behind-the-scenes math and unit manipulation, we get the following equation, where density is represented by the Greek letter rho. On the instrument panel of an airplane, an instrument called the barometer would not be found. So why so much emphasis on pressure? Well, the altimeter is actually a barometer that displays information as altitude versus pressure. Although pilots refer to flying around at a constant altitude, such as 6,000 feet, they are actually flying around in an area of constant pressure. When a pilot adjusts the altimeter to the local altimeter setting via the Kollsman window, they are calibrating the altimeter to the pressure in the general area. This is why, when flying long distances, it is important to update the local altimeter setting, as the pressure could have changed and actual altitude could be higher or lower than indicated. Now that we have established that pressure is constant, as well as the ideal gas constant, the only values that can change are temperature and density. Temperature and density are inversely proportional, which means that if one value increases, the other must decrease. This is why, as temperature increases, the density of air decreases. Recall that density altitude is defined as the pressure altitude corrected for non-standard temperature. To find this correction, we use a density altitude chart. Using this accident as an example, we know that airport elevation is 6,370 feet. The temperature is 84 degrees and the altimeter setting is 3000. First, we need to find the pressure-altitude conversion factor from the right side of the chart. Find the altimeter setting of 3000 inch mercury and move over to the right to find a PA factor of -73. Subtract this number from the airport elevation to get 6,297 feet, which we will round up to 6,300 feet. Now, go to the bottom of the chart to the outside air temperature of 84 degrees. From here, go straight up until they intersect at the 6,300-foot diagonal line. Move horizontally over to the left and note 9,300 feet as the approximate density altitude. Referring back to the column of air, let's zoom in to see the air molecules. At sea level, the air is dense and air molecules are packed tightly. As we climb higher in altitude to 5,000, 10,000, and 15,000 feet, we see that air becomes less dense. By comparing a cubic foot of air at sea level versus one at 10,000 feet, we see that for the same volume, the air at sea level is more dense. Why do people describe density altitude as the altitude the plane thinks it is located? Using what we calculated before, an airport with an elevation of 6,375 feet would have a density of molecules that looks like this. However, we calculated the density altitude to be 9,300 feet. By taking into consideration density altitude, we are saying that the air surrounding the airplane at airport elevation would have the same air density that would be found at 9,300 feet. To think of it another way, it would be as if someone moved the runway up to 9,300 feet. It is this low-density, 9,300-foot-like air that affects aircraft performance and has significant impacts on the lift generated by the wings, the efficiency of the propeller, and the power output of the engine.